In this section of introductory algebra, we're going to be talking about graphing, things including the coordinate plane, graphing points, graphing equations, and finding points of intersection. So the Cartesian coordinate system, it is very unlikely that you are in this class and you have not seen this before, but I just thought it would be worth reviewing. The coordinate plane that we graph points on, that we're used to doing that on, that is called the Cartesian coordinate system. Another word for it is rectangular, and call it rectangular because each point that we put on it has essentially like a length and a width dimension, like a rectangle would. It has a horizontal kind of piece of information and a vertical piece of information. The horizontal piece of information is called the x-coordinate, and the technical term for that is actually called the abscissa. That is a word that you will not hear very often. I have very high-level math students who don't know what that word is. And the vertical piece of information is called the y-coordinate, and the technical word for that is called just the ordinate. Together, they are two pieces of information, or coordinates. The place on the Cartesian coordinate plane where the x-axis and the y-axis intersect, right here, is called the origin, and the coordinate points of the origin is 0, 0, because at the origin you have gone precisely nowhere in the x direction and nowhere in the y direction. We call the direction of right in mathematics, to the right, we call that the positive direction. To the left is negative. Similarly, up is positive and down is negative. And so, if we wanted to graph a point, just as a quick example here, we'll do more later, but if we wanted to graph the point A, and we knew that that point was at, I don't know, let's say -1, 6, what that means is, because this is our abscissa and this is our ordinate, henceforth just the x-coordinate and the y-coordinate, we would be able to go to the left in the x direction, the negative x direction 1, and then up in the positive y direction 6. So 1, 2, 3, 4, 5, 6. So that point right there would be point A, and the coordinates of point A. Let me write that in a slightly different way. Sorry. The coordinates of point A, as we said, were -1 and 6. Okay, that's how you graph that's how you graph a coordinate on a Cartesian coordinate plane. And you can think of it also, because if we went to the left a little bit and up more, that looks like now a rectangle. Everything has a left and right piece of information and an up and down piece of information. Now this coordinate plane, this rectangular coordinate plane, has this funny name, Cartesian, because of this guy. This guy is René Descartes. In the story of math, there are a few very prominent characters, and I don't know that any are quite as prominent as this guy. Not only is he obviously the most handsome man in the history of mathematics, but we owe so much of the foundation for what is modern mathematics to him, because he's responsible for developing this Cartesian coordinate plane upon which we have based all of analytic geometry. Analytic geometry is a fancy word for how we can kind of model or show these abstract things like equations and like the relationship between different numbers and stuff, how we can show them visually. That is so very important because it allows us to contextualize these abstract scenarios that we often come across when we're doing math. He's also got a lot of other achievements in mathematics. He's the person who standardized superscripts. So like the reason we say x times x, we can represent that as x squared, where that 2 is up in the superscript, is because of him. He also basically formalized x, y, and z being the common mathematical variables, and that's because they play quite well in his coordinate plane. Anyway, if you ever see the word Descartes or Cartesian, this guy, just think of this guy. Just think about his eyes and how dreamy he is. He lived back in the early 1600s. And there was lots of math that happened before him, but all the math that happened since him includes things like all of calculus, of which so much is based on the Cartesian coordinates, and more. Anyway, that's enough about Rene Descartes. If we just want to go about the business of graphing points, we can do that pretty easily here. So point A here in red, it's this positive and positive, right? So we're going to be positive and positive. We're going to go to the right one and up two. Now, something I forgot to mention is that we have a way to distinguish between the four quadrants of the coordinate plane. So this top right quadrant where we have positive and positive values for x and y, that's called coordinate 1. We use Roman numerals to instead of digits, instead of like actual written numerals for these quadrants. Quadrant 2 is the top left quadrant. That's the one that has negative x values and positive y values. Quadrant 3, which is my favorite quadrant, because when you write the negative comma negative, it looks like a sleepy face. That's in the bottom left. And then quadrant 4, which is in the bottom right, is when you have positive x values and negative y values. And that should intuitively make sense to you. So we put point A on the graph, and point A is in quadrant 1. Okay, point B, negative 2, 5. So if we go 1, 2 over, 1, 2, 3, 4, 5 up, there we have the point B, which is at negative 2, 5, and that is in quadrant 2. And then the last point here is point C, and point C is in is 3 comma negative 2. So 1, 2, 3, 1, 2. So we always read the x coordinate first, which is very important because x coordinates tend to be another term we use to describe x coordinates are independent. We call it the independent variable if we're looking at variables x and y. And that will come up in our next little thing here where we talk about graphing equations. So this method we're going to look at right here, no matter how much math you know and how advanced and what math class you're in and what crazy looking equation, as long as it's a rectangular equation that you are asked to graph, no matter how complex, you can always use this strategy to graph something. And that strategy is to simply create a table of values or a chart showing the values. Now, in order to do this, it's important to consider what is the number or what letter, like we have x and y here, which one are we going to be plugging in? Like what's going to be plugged in order to get something else out? So one of these numbers is an input and the other one is an output. We will talk a lot more about that relationship when we discuss something called functions, but for now what we're doing is we're going to create a t-chart where I'm going to plug in numbers for x and I'm going to get numbers out for y, and the way I'm going to do that is to say, well, y is equal to 2x minus 3. So let's just see this. I'm going to plug a number in and it'll hopefully make sense, okay? It'll hopefully make sense what we're doing here. So I'm going to plug in and how do you know which numbers to plug in? Well, if you look carefully here, I'm going up to positive 10 and down to negative 10 in each direction from the origin, right? The origin again is 0, 0. So I certainly am not going to pick x numbers less than or greater than 10 or less than negative 10. So why don't we pick some that are close to 0? Why don't we pick 0 also? That's a great number to pick. That's the best number to probably start with, in fact. So let's plug in 0 for x. If we plug in 0 for x, that means 2 times 0 minus 3. That's just negative 3 because 0 times anything is 0. So 0 minus 3. So that point 0, negative 3 is on the graph of this equation. 1, 2, 0, sorry, 0, negative 3, 1, 2, 3. Okay, so that point is on there. Awesome. Now, let's pick another point. Let's pick 1. Okay, if we plug in 1 for x, then it would be 2 times 1 minus 3. That's going to be negative 1. 2 times 1 is 2 minus 3 is negative 1. So that means the point 1, negative 1 right there is on this graph also. Now, we only need 2 points to define a line. So if you have a straight edge, you can put them on there. But just for the sake of practice, you put the straight edge where it touches both those lines and you draw that line. But for the sake of practice, let's plug in one more number. Why not 2? We could have also plugged in negative 1 and it worked just the same. So 2 times 2 minus 3. So that's 2 times 2 is 4 minus 3, and we're left with 1. So that means the point 2 comma 1, 2 comma 1 is also on this line. And if you look at this, and I'm going to do just the worst job ever of drawing in this straight line here, but this line should look something, oh my gosh, something like that. It's not a very good. I have it better on the next slide. Imagine that red line goes through those 3 dots. Okay, now we can do the same thing for this other equation. Okay, x, and then this is negative x plus 6, and so whatever comes out of that is y. All right, so we're going to plug in, let's plug in the same numbers. Why not? Plug in, sorry, let's use blue for this. We're going to plug in 0, 1, and 2. Sure. So we got negative 0 plus 6, that's just 6. Negative 1 plus 6, that's 5. Negative 2 plus 6, that's 4. So let's plot these points. We got the point 0, 6, we've got the point 1, 5, and the point 2, 4, all on this one line. And you don't, again, you only really need, if you know you're dealing with a line, you only really need to plot 2 points. Okay, so anyway, 0, 6, 1, 2, 3, 4, 5, 6. 1, 5, 1, 1, 2, 3, 4, 5. And 2, 4. 2, 1, 2, 3, 4. So something went away with my other one. Okay, and then I'm going to do just the worst job again of drawing this line in. Ah, man, it's pretty bad, but it's okay, okay? You get the idea. That line is supposed to go through those 3 dots and continue on forever. Lines, when you draw them, lines are continuous. There's no number you can plug into a line where you wouldn't get another number out. Or more accurately, there's no number you can plug into the equation of a line to get no number out. Therefore, lines are continuous. They need to have arrows on the end of them. Okay, so that's how you would graph a line. And this strategy of making these charts here, this will always work. It doesn't matter how complicated your equation is. If you had something like this, you could still graph that using that same strategy. And the last thing we're going to talk about are finding the points of intersection. A point of intersection is quite plainly where on the Cartesian coordinate plane do 2 curves, because a line can be a curve, it just doesn't have any curves in it, or 2 lines, or 2 equations, or the graphs of 2 equations, or more equations, where do they intersect? Well, for this one, we can see quite clearly that they will intersect at the point 1, 2, 3, 1, 2, 3, so it intersects right here at the point 3, 3. Now think about, because we know about ordered pairs, we know that 3, 3 represents the x and y coordinates, or the abscissa and the ordinate. And we know over here that we have x and y's also. So if we were to plug in x and y into either of these equations, why not try both, right? So if we plug x and y in here, we will have 3 is equal to 2 times 3 minus 3. Yeah, it does. Of course it does. It should. It should always do that, right? If it didn't, we would have concerns, because otherwise it would not be on this line. And it works for this one too. 3 equals negative 3 plus 6. Yeah, negative 3 plus 6 is 6. It is actually the case that that 0.33 is the only, those values for x and y are the only values for x and y that make both of these equations true at the same time. And that is a very interesting point to make. When we get into something known as systems of equations, we can solve this. We can find the value of 3, 3 without doing any kind of graphing whatsoever. And that the method we'll use for that is something called substitution or Gaussian elimination, or we can also graph, and like we just did. So it's something to look forward to in the future, but for now that will end our very basic discussion on graphing things on the Cartesian coordinate plane.